Hello and good morning to everyone. My name is Giorgos Prionistis and I would like to present our work called Voltage Stability Support offered by Active Distribution Networks. A work that I did in collaboration with Professor Costas Vournas and Theodoros Souxes. So, the main aim of this paper is to investigate the effect that distributed generation can have on the system's loadability margin, considering that distributed generation, especially on the distribution side, is constantly increasing. So, with the introduction of the active distribution networks, we aim to create a control scheme for the active distribution networks in order to increase the loadability limit of a power system. And for that purpose, we performed a two-stage optimization, one on the system side and one on the distribution side. The results of the control scheme are evaluated on a small test system and on the Hellenic interconnected system. The two-level control approach, which is shown in the figure, is divided into a transmission system and its controller and multiple distribution feeders that are connected to the transmission system and inject active and reactive powers to the transmission system. So the control scheme includes an upper level controller located in the energy management system and a lower level controller by the distribution side. In the EMS, for each snapshot taken by the state estimator, a voltage stability assessment problem is solved, and for each solution we can calculate the maximum power transfer and the sensitivity coefficients, which are then transferred to the local active distribution network controller in order to regulate its components and calculate the active and reactive power injections that need to be injected to the transmission system in order to maximize the loadability margin of the transmission system. So the calculation of the maximum power transfer and the respective sensitivity coefficients are computed from a central optimization problem where the objective function is the maximization of a stress function as shown in this equation for a specific stress direction, subject to the equilibrium equations of the power system. And the solution for each contingency provides the maximum power transfer and the sensitivities which correspond to the Lagrange multipliers of the optimization problem. All this data is then sent to the local controllers of the active distribution networks in order to regulate its components. As an active distribution network in this work, we consider a network with some or all of these available controls, which are used as control variables, which can be switch stand capacitors, load tap changer, inverter-based generations, battery energy storage system to control the active power, and dispatchable loads. Concerning the local control problem, in the distribution side there are two different problems that are to be addressed. The first one is to maintain the filter voltages inside the operating limits, subject to the inequality constraints for the available control variables, such as the reactive power generation according to the capability limits of the inverters, as shown in this equation, and the minimum and maximum tap ratio for the LTC. The secondary objective is to use these available controls in order to maximize the system loadability margin and support the transmission system. As for the inverter-based generation and reactive power and voltage control, there are three different kinds of controls that are assumed. The one is unity power factor, where actually there is no control available. The second one is a QV control, according to a QV characteristic for each inverter-based generation, where the reactive power is dependent on the voltage at the point of common coupling of its PV. The third control is the constant voltage control, where the voltage at the point of common coupling is used as a control variable and is set to 1 per unit to maintain voltages under normal operating conditions and 1.05 per unit to support transmission system in case of emergency conditions. So two different control schemes are assumed. In the first one, the local controller in the distribution side accepts the Lagrange multipliers that are calculated in the EMS, and using a simple linearized objective function is trying to maximize the maximum power transfer, always subject to the distribution feeder constraints. In the second one, we can calculate a priori the active and reactive injection limits subject to the feeder's constraints and provide this information to the EMS, so it can solve the voltage security assessment having this information, and after solving can provide the set points to the local controller. In the case studies that were studied in this work, both schemes provided the same results. The first case study was performed on a small transmission corridor that is connected to a load, and in the middle of the corridor there's a distribution feeder, a medium voltage distribution feeder connected through a transformer with a load temp changer, and on the feeder there are three photovoltaics assumed. So the control scheme distinguishes between the transmission system and the distribution feeder. As seen in this figure, the range of the active and reactive power injections is formed for variable LTC set point from the maximum to the minimum value, and for variable active power generation for different types of reactive power control for the inverter-based generation. In this figure we can see the two different PQ ranges for unity power factor and for the QV control. Similar ranges would be saved for constant voltage control for each voltage set point given. So after obtaining this possible range, it is easy to maximize the maximum power transfer with respect to the Lagrange multipliers that are sent by the VSA solution. After obtaining the optimal set points in order to maximize the maximum power transfer, we used these set points in a quasi-steady state simulation where we considered constant active power from the distributed generation and a variable load conductance in the transmission system with a constant, which is increased with a constant rate. So in the figure, we plot the load bus voltage against the active power consumption for the two different inverter-based generation controls. First for the unity power factor, and then for the QV characteristic. We can see a minor increase in the maximum power transfer for the use of the QV, and in that sense we created a kind of emergency control, so when the voltage of the high voltage side bus drops below 0.9 per unit, we set the LTC set point to the minimum, and when we assumed constant voltage control for the inverter-based generation, we set it to the maximum. So in the same plot we can see an even greater increase in the maximum power transfer, and with the blue dot we can see the point that the emergency control was enabled. The proposed control scheme is then implemented in the Hellenic interconnected system for a specific snapshot that was taken by the state estimator for June 2010, where a peak load was observed, and the voltage security assessment showed that for a loss of a generating unit in the Peloponnesian area, the system would become insecure. For the simulation of this snapshot, we performed a quasi-steady state simulation using the WP stub environment, and we observed the Lagrange multipliers of active and reactive power injections at each bus. So in the next figure we can see the post-contingency loadability limits for the total active power consumption of the area of Peloponnesus versus the voltage of the characteristic bus of methanol. It can be seen that the maximum possible consumption is reduced after the contingency, meaning that the system is unable to restore the load, eventually resulting into a collapse. The maximum power transfer for the area of Peloponnesus was computed to be 8 for 1.5 megawatts. In order to implement the aforementioned control scheme, we replaced for medium voltage side loads with the model test feeder, and in order to do that we created a ranking index that is based on the Lagrange multipliers and the change of active and reactive power that would be injected by the test feeder for each kind of control. So the 4 buses with the highest index were replaced with the test feeder and scaled to match the original bus load. For these last 3 simulations, we assumed the constant voltage control, setting the set point of the PVs equal to 1 per unit, obtaining a slight increase in the maximum power transfer, and then we did the same assuming LTC set point reduction to the minimum, obtaining even greater maximum power transfer for the area of Peloponnesus. And as a last simulation, we set the voltage set point of the PVs at 1.5 per unit, which is the max permissible voltage, and the LTC to the minimum, obtaining even greater increase in the maximum power transfer. These 3 controls that were implemented are shown in the same figure, together with the base case scenario, where it is noted that with the latter control, the maximum consumption in Peloponnesus becomes comparable with the pre-contingency load. So a lot of conclusions can be drawn. I think the most important one is that even with just a few buses replaced with the test feeder, it is possible to achieve a quite significant increase in the maximum power transfer that can be significant in cases of an emergency. So I think there's a lot of possible future work that can be done in that area. That could include more information about storage systems, dispatchable loads, the general optimization, including active distribution networks, maybe some probabilistic approach, considering that many of the variables are like distributed generation, are highly based on probability, and in order to achieve all this, there has to be some communication between the transmission system operator and the distribution system operator. So this area is also very important to be studied. Thank you very much for your time.
Thank you, Giorgos, for the presentation. And Giorgos is now available for questions. And I have already a couple from Hossein Sekavat. I'll do them one by one. While computation, the loadability margin at the EMS level, what assumption do you take for the power injection set points from the ADNs? That's the first question. During computing the loadability margin at the EMS, what do you assume concerning the injection from the distribution network?
Do you mean if I assume that they are constant during the computation?
Yeah. Do you assume they are constant?
No. I mean, during the quasi-steady state simulation, they are changing. When performing an optimal power flow problem, they are considered constant. It depends on the formulation.
The second question is, under which conditions the calculated sensitivity coefficients are valid for the calculation? Because they sensitivities.
Okay. This is an interesting question because the sensitivity coefficients are evaluated at one specific operating point. Then maybe we change the set points, actually again changing these sensitivity coefficients. So we try to iterate this until there is a kind of convergence, so that we use the correct set points that correspond to the correct sensitivities. But because the transmission system is very large compared to the distribution feeders, this change in the sensitivity coefficients between the operating points was insignificant.
Okay, thank you, Giorgos. One more question. This work assumes that active distribution networks can support the secure operation of bulk transmission system, which is true as long as VAR voltage control variables are concerned. However, regarding the active power of distributed plants, there should be a trade-off between bulk system security and the need to avoid renewable energy curtailments. So the question is how the support given to the transmission system is linked with renewable energy safe consumption in the feeder.
I don't quite understand. I mean,
let me try to answer this. The idea here in this paper is that the feeder is first kept within acceptable voltage levels, and then any available injection of active and reactive power can be given to the transmission system. Okay.